Yeah, first I'd like to thank Joe for inviting me to this wonderful workshop. I have enjoyed the module 1 and module 2 already. So today is my turn to make a real contribution. Yeah, thank you, Joe. The talk is Renaissance of phase. Everybody is familiar with phase. It's really, it's a very ancient topic, even more ancient concept. Of course, today I'm going to talk about something new. We start with matrices. Well, actually, I start with something even simpler than matrix, a scalar. If you have a complex scalar, you can write the C in the polar form. Right? So the polar form consists of the magnitude and the phase. So for scalar, this can be traced back probably for over 300 years. The important property of this magnitude and phase are as follows. If you have the product of two complex numbers, you look at the magnitude, you see the magnitude of the product is equal to the product of the magnitude. The phase of the product is equal to the sum of the individual phases. So from these basic properties, you see that when you manipulate numbers, especially when you try to calculate the product of two numbers, this polar form actually makes it easy. So now let's ask this question. What are the magnitudes and the phases of a complex matrix, n by n complex matrix? So the magnitudes actually have a good answer, a well-accepted answer. So if you have a matrix C, you carry out the SVD, singular value decomposition. With a U and a V unitary matrices, and a sigma in the middle. Sigma is a diagonal matrix. The diagonal elements, okay, are called singular values. So you can take those singular values and consider them as magnitudes of the matrix. So you have a n by n matrix, you have n magnitudes. You usually put this magnitude in the vector. You get you order them from the largest one to the smallest one, right? So you will see that those singular values are very, very useful. You see, singular values almost everywhere. Single processing in data analytics, in control theory, everything, everywhere. So especially, the largest one, the smallest one, are particularly important. So what are the nice properties of singular values? Well, there are plenty. But one important property is that the singular values actually give bounds on the eigenvalue magnitudes of the matrix. So all the magnitudes of eigenvalues are bounded, right, by the singular values, by the smallest one from below, largest one from the top. Also, if you are interested in the singular value, the largest singular value of a matrix product AB, then you can bound this by the product of the largest singular values of A and the largest singular value of B. From below, you get something similar. If you really want to find a lower bound of the small singular value of AB, then you have something similar. The number of non-zero singular values is the rank of the matrix, right? That's so nowadays people are talking about when you talk about the rank, they use this very important concept called zero norm. Zero norm is simply the number of non-zero elements. So that's a rank. And this kind of concept is widely used in compressing data, compressing information compressing. So there seems to be a nice understanding on matrix magnitudes. So what are the phases of a matrix? Well, this question has been asked for many, many years. Actually, there was some kind of earlier attempt to define phases. What people do is that they look at a matrix C, then they take the polar decomposition. They feel that, okay, the polar decomposition is similar to the polar form of Compton number. Then, of course, from the polar decomposition, you have a positive definite part. Then you take it as a kind of a magnitude. This unitary part, you take it as a phase. Then you, of course, then you can say, okay, the phases, the so-called principal phases of matrix C, can be defined as the angle, the argument, or say that the phases of the eigenvalues of the unitary matrix U. Okay, some people took this definition. Then they try to see, use this definition, use these the principal phases to analyze, to do matrix analysis. But it turns out that this is a messy thing. It's not very pleasant. So this the phases, the so-called principal phases defined this way, is not easy to use, and it doesn't have the right properties. What we can do now, we try to define the phases in a different way. First of all, we look at the concept of numerical range of a matrix. The numerical range of matrix is defined this way. Basically, you look at the quadratic form, x star cx, for all x in the unit sphere, complex unit sphere. Okay, look at all the scalars, all the quadratic form you get. This form a set in the convex plane, and this set is called the numerical range of the matrix. So this set is actually is nice. It's convex set, it's compact set, and it looks like something like this, the numerical range. It is well known that the numerical range actually in this set contains all the eigenvalues of C. So all the eigenvalues are inside. So and this of course this compact set can be anywhere in a complex plane. But there's a special case. The special case is that when this origin is outside the complex set, that means the complex set is away from origin. In this case, we say the matrix is sectorial. No, the matrix is sectorial. Why sectorial? Because this is contained in a sector, or say this is contained in the half plane. In one side of a half plane. Yeah? So if a matrix is sectorial, just like this, your WC is away from origin, then C has a unique so-called symmetric polar decomposition. Now we just forget about the original polar decomposition. We look at the symmetric polar decomposition. Okay, the decomposition looks like this. The C is written as a PUP. So U is unitary and the P at two P's in both sides. So that's why it's called a symmetric. The P is not in one side. P is actually just a positive definite matrix. So after you carry out this decomposition, then you define the phases of C as the eigenvalues, as the phases of the eigenvalues of U. U is unitary matrix, so all the eigenvalues are distributed in a unit circle, right? So they have phase information. They don't have magnitude information. The magnitudes of the eigenvalues are all equal to 1, but the phases they have a different angle. So then you define the phases of a matrix, of a sectorial matrix in this way. Okay. So the key is that you need to do this symmetric polar decomposition. I'm not going to go into the details on how to do this symmetric polar decomposition, but I just want to give us some kind of rough interpretation of the phases, especially the largest one and smallest one. So you have a numerical range here. You draw a sector. You draw a sector covering numerical range as tight as possible. Then this lower ray gives the smallest phase, and the upper ray gives the highest, largest phase. So the other intermediate ones, they are in between, but they are not, they're less important. So let's just focus on the largest one and the smallest one. Okay, so largest one and the smallest one, those phases, they can be obtained from the numerical range rather easily. So why those phases are important or useful? Okay, one thing you can say is that the phases of eigenvalues of C, the eigenvalues are all complex numbers. Some are small, some are big, right? The eigenvalues, they are complex numbers, so they don't have individual phases. Those individual phases are all bounded below by the smallest phase of C and bounded above by the largest phase of C. So the largest phase and smallest phase actually give an estimation on the eigenvalue phases. Okay. You can also, you've got a bunch of phases. You can also look at the number of non-zero phases. We define this as the phase rank of C, or we denote it by rank, P rank. As we said, this polar decomposition or the polar form of complex number is very useful in investigating the product, matrix product. Well, what can we say about the product? If you know the phases of A, you also know phases of B. What can you say about the phases of AB? Well, you wish to get this kind of understanding. And the intuition, of course, is from the scalar case. It turns out that they can say nothing. That was a rather negative, conclusion. But the thing is that that was the wrong question to ask. The good question to ask is, is to try to say something about the eigenvalue phases of AB. If you take a step back and try to ask this question, what can you say about the eigenvalue phases of AB? Then immediately you get this estimation, or say this upper bound and lower bound. So that certainly, well, it turns out that this is, those bounds are very important. So up to this point, probably we can all appreciate that matrix phases complement matrix magnitude. So this is basically the phase and magnitude are two sides of a coin. Combined, they give a more complete picture of a matrix. So if you want to do matrix analysis, in the old days, if you only use the magnitudes, the singular values, you can say simple things, but rather incomplete, I would say. With the addition of phases, you probably will get much more information out of a matrix. Okay. So the magnitudes, namely the singular values, are extensively studied and widely used. Nowadays, when you talk about the data, big data, whatever, without single values, probably cannot say anything. Little is known about phases. So phases is still kind of a new concept. We have some basic definition and understanding, some basic, some preliminary results. Well, I think you know, there are still plenty of research opportunities ahead of us. So let's maybe again look at kind of an example. You know, in many situations, we are interested in the invertibility of a matrix like this, I plus AB. We want to see if this is immutable. We can do gain analysis. It is well known that if the largest magnitude of A times the largest magnitude of B is less than 1, then this matrix is definitely immutable. So this is some kind of you know, small gain theorem or you know, or gain analysis. You know, it's easy to prove. Now with the addition of phase, the phase concept, we can say something similar actually. I plus AB is invertible if the phase of A, the largest phase of A plus the largest phase of B is upper bounded by pi. The smallest phase of A and the smallest phase of B added together is lower bounded by minus pi. Then we get the invertibility of A. You might want to combine this gain analysis and a phase analysis together. You can have some kind of mixed analysis. That's again provide for you to study. You know? Okay. Yeah. So now we have you know, from a matrix level, we have introduced this new concept of phases. And we are able to say something. Huh? So maybe you'll say, okay, in the data science, you can use these matrix phases to indeed analyze data. What's data? In my mind, the data is just matrix. At least in a lot of situations, for example, image or whatever. So I would speculate that phases will play an important role in future data science. Today, probably I just then go back to my old profession, system theory, control theory, and see how the phases can be used to study systems. Let's maybe give a kind of a brief historical review on the use of phases in signals and systems. Well, as a signal system and control theory, probably the whole development lasted 200 years, probably up to now. So early, you know, we have Fourier transform. We use Fourier transform to analyze signals. Right? Signal is also data. And then later on, we talk about about frequency response. You know, we use border plot. Later on, then you know, you have a filtering problem and control problem, robust control up to now. You know, in the first 150 years, actually phase played a rather important role. The reason is that you know, there in the first 100 years or 150 years, we play with the complex numbers. We represent a system using a frequency response, which is also a complex function. So then you know, this of course, we talk about a scalar system. Then of course, and then just like a complex scalar, and then phase is ready to be used, and it's found to be very useful. The thing is that you know, when we got into the multi-variable system time, the role of phase become less and less, diminished. You know, starting from LQG control, even in robots control, small gain theorem. So you have small gain theorem, but that time was nobody knows what the small phase theorem. This this history actually lasted until very recently. We found this the new definition of phase. Found that now in this new era, this phase will play a complementary role as a gain in system theory, in control theory. So you will see, briefly see it in the next few slides. Everybody knows body plot, body diagram. Say, in the old days when control theory, we study control theory, we have this body magnitude plot and also phase plot. These two plots are actually, they always come together. They're say shooter to shooter. They have to be used as some kind of simultaneously used all together to do analysis and design. For a multivariable system, MIMO system, well, we can actually plot the magnitude plot. Just plot the singular values. This is implemented in MATLAB, actually, but there's no phase plot for MIMO system. Now, suppose that you have a system, we say it's G. Why don't we just plot the numerical range against the frequency in the compass plane? We know that the frequency range, the numerical range is a set, right? So at each frequency you get a set. Then change the frequency, you draw this. So that's considered to be a generalization of the Nyquist plot. Actually, you can plot it. So this system G is said to be frequency-wise sectorial. If Gj omega is sectorial for all omega, for all positive frequency. So if you look at this system, is this frequency-wise sectorial? Actually, it's very close. The only problem is that the origin is here, see? And then all the other low frequency, the numerical range is away from the origin. But somehow when you get into high frequency, this is approaching the origin. So it's not quite frequency-wise sectorial, but it's close. Now, suppose that you have a frequency-wise sectorial system, then of course then you can compute the phase at each frequency. The phase is a vector. Actually, it's a vector valued function. You see that you can plot. You can plot like this body phase plot. This then this complete the complete body diagram for MIMO system. Okay, for phase we define this the H infinity phase sector of a system G as follows. Right? So suppose that G is a frequency-wise sectorial. Then you look at the smaller phase, then take a inf for overall frequency, then you get the number. For the larger phase, you take a suit, then you also get another number. So basically, after you take the inverse suit, you get the interval. So the interval can be also considered as a sector. So this sector is called the H infinity phase sector of this system. So corresponding to the H infinity norm of the system, now you have a H infinity phase sector. So you can actually read out the phase sector from the phase plot. You just look at the horizontal line from below, and look at the horizontal line from top. You just just try to squeeze as much as possible. Then indeed you get this here. And this is in a similar way as H infinity norm, which can be read out from the body magnitude. So if a system has H infinity phase sector of beta, that means the frequency response is always bounded. It's in this dark area. So alpha is this angle, beta is that angle. Then your frequency response is in this shaded area. And the shaded area can be even like this phase sector can be longer than pi. So it actually looks like this. That's also possible. So it turns out that this phase sector thing, the H infinity phase sector thing, subsumes the usual positive real system concept and the negative imaginary system concept. So we have a positive real system, meaning that all the frequency response is in the right hand compass plane. We also have negative imaginary systems whose frequency response is below it's always below the real axis. So with the phase concept and the phase sector actually cover those situations as special cases. Okay, now let's try to study system stability, closed loop system stability using phase. We have a feedback system with the two components, G and H. We want to see if this system is stable or not. It turns out that this system is stable if the determinant of this I plus GH is not equal to 0 for all S in the right-hand side of compass plane. Right? So this I plus GH is something we have seen before. We look at the I plus AB. So this I plus GH actually is just for fixed S. Of course, you get I plus AB business. So you want this to be basically you want this matrix to be non-singular. Then we can use gain analysis. Gain analysis is that okay, make sure that all the eigenvalues are inside the unit circle. Then that makes the eigenvalues of a GH are inside unit circle. Then definitely I plus GH is invertible. So that gives a kind of a small gain argument. Then you can also require that the phase, the eigenvalue phases of GH to be bounded away from the real negative real line, negative real axis. So basically, you can be anywhere in the plane except the negative real axis. This is kind of a phase argument or phase analysis. So from the gain analysis of phase analysis, you can obtain the so-called small gain theorem, which is stated here. The idea is that make sure that the gain of G or the magnitude of G and the magnitude of H multiplied together is less than 1. And your even shape the system is stable. This is well known. This has maybe even a 50-year history. This is new. Small phase theorem is new. It says that if you really want to see, you make sure that this system is stable, then you can just look at the phases of the individual components. As long as the phases are added together, it's bounded above by pi and bounded below by minus pi. And then you take 50 years for the small phase theorem to meet that small gain theorem. Motivated by the small phase theorem, of course, we can also talk about the phi infinite control. Basically, we try to design controllers to satisfy kind of a phase requirement. And you can pose the problem in a similar way as H infinity control. So in H infinity control, we try to minimize the norm. Here, we just try to make the phase desirable by designing K. So then this design problem is open. It's completely open. We'll say, we have some several directions to go, but at the moment we haven't really gone into this those research directions yet. We just propose it here. If any of you is interested, you can indeed look at those problems. So here comes the recap. We see really the birth of a phase theory in this moment. We have a look at the phase of a matrix, or say phases of matrix. We'll also look at the phase of LTI MIMO system. And recently, there are some other studies. So we can talk about the phase of a graph, a network, a dynamic network. We can also look at the nonlinear systems. We can define phases. So those are, actually the concurrent, like a continuing work of this phase theory research. Well, we have quite a strong and large phase theory team. Really, I really wish to thank all these people here who have made big, significant contributions to the development of a phase theory. And the research is still going on, and I think it will last for many years ahead of time. Well, that's what I have to talk about today.